Our second talk this morning is by Giancarlo Urzúa on wormholes in the moduli space of surfaces. Giancarlo?
Thank you very much for the introduction and for the invitation. I will open the chat in case you want to ask questions. Okay, so I will talk about this thing on wormholes in the moduli space of surfaces. And this is a joint work with Nicolás Vilches, who used to be my student here, a master's student in Chile, but now he's in Columbia University. So okay, let us start. So our ground field, as in the whole conference, is C. So you can see everything and everything is okay, right? Yes.
That's fine.
Okay. Okay, so mk squared chi is going to be the moduli space of canonical models of smooth projected surfaces of general type with invariance k squared and chi fixed. Okay. And as Sonke said, this is inside of the Kollár Shepherd-Barron Alexeev moduli space of stable surfaces for those invariants. And I will care about the closure inside of that moduli space, which is this. I think that people call it, and Sonke did it, the main component or the main components inside of the KSBA moduli space. Okay, so this wormhole phenomenon will happen here. And I will explain it with a picture right now, and then with an example. This is the picture. So here you have the closure of the moduli space. So this is the moduli space for canonical models. And this is supposed to be like the boundary that you get when you closure. So the situation is the following. You have like a disk that goes to the boundary, like in here, where, so this represents a certain degeneration of smooth surfaces to a surface that is normal projective with only wall singularities. Okay, so that is the starting point for the wormhole. Now I was worried about wall singularities. It seems like people maybe didn't define it, or they did, but I don't know if you remember that. So what I just did was to include a definition here. So if A and N are co-prime integers, then the cyclic quotient singularity that has this type is what we call wall singularity. So 1 over n squared, 1 and a minus 1. And these are exactly the cyclic quotient singularities that admit a smoothing and turns out to be one-dimensional that has Milnor number 0. Okay, so those are the wall singularities, and they are pretty important in this moduli business. So now you have the situation, the first degeneration, and then there would be like a surgery on this surface that will move you to another place. That is why we call it wormhole. And where you will get another degeneration that ends in this other surface. And this other surface is also a normal projective surface with only wall singularities. So I will explain what I mean by this wormhole move. Okay, but okay, so that is the picture. We will propose a general conjecture that tells you that we will always move inside of the same moduli space. So we don't go to another moduli space, and that is why we call it wormhole, like this is the universe, and you stay there. So the questions are, for example, we can prove that in many cases, but not in general. So existence in general of this situation, that is what we expect. I will be precise in a moment. Yes?
A question, you say in the same moduli space, do you mean in the same irreducible component? Or?
No, and that is one of the points. So maybe we move to another component, but with the same invariance, k squared and chi.
Right.
And that is the other point. Like, when do we move between irreducible components? That would be like an application. How to guess how to know when we move. This is the example for the whole talk. So we take the modular space of these famous Godot surfaces, and that means, yeah, you can see that k squared equals to 1, k equals to 1, that implies pg and q are 0. Okay, so that is going to be my modular space where I will construct an example of a wormhole. As you know, mice read expects this M11, which is this for 11, to be 5, so to have 5 components labeled by the fundamental group. This is the topological fundamental group that should be simply connected, set 2, set 3, set 4, and set 5. And we know that that is true from 2 to 5. The latest news is 2. We know now that there is only one irreducible component. That is a work of Diaz and Rito the last year. And also in Simply Connected now, there is at least one explicit, it seems like there is at least one explicit component by, and I Schreier and Steger, I think, and also last year. But we don't know if there are more in the case of one. So this is true now from 2 to 5, and 1 is still open. Okay, that was just a comment. I will take an example from our paper, Diaz, Rito, and me, last year, a year ago, where we have an analysis of wall degenerations with wall singularity for set 2 Godot surfaces. So for the surfaces that have fundamental group set over 2. And I don't know, I was going to share the link to that paper. Wait a second. In case you want to see more details. So there we go, section 2. I'm coming back to the example. So the example is the following. You start with an Enriquez surface. So you know these surfaces with PG equals Q equals 0. So that twice the canonical class is trivial. So we have an Enriquez surface that is my S with a configuration of -2 curves. That means P1 with self-intersection -2. That intersect exactly in the way that you see here. So you have these nodes, 1, 2, 3, 4, 5 nodes. Okay, they exist, and you can see that in this paper, section 2. You produce those surfaces through a double cover of P2 with certain ramification on a branch curve. And then what I do is to blow up. So this is the Enriquez. So now you blow up 5 times. I think that you do it 3 times here in this node, at this node, and once here and once here. So over 3 nodes, you blow up 5 times. And now this -2 becomes a -4. This other -2 becomes a -4. This -2 becomes a -5, and you get 2, 2, 3, 5, 4. It's a chain of P1s and another -4 curve. Now, again, since maybe you are not used to wall singularities, I can say the following. I added this minutes ago. If you start with, so to get in, this is the minimal resolution of a wall singularity. So the question is how you get all the minimal resolutions of wall singularities. So this is the algorithm. You start with 4, and then you have this algorithm, and where you add a 2 on the right or on the left at the end. And on the other side, you add 1. So from 4, you go to 5, 2. And then from 5, 2, you have 2 possibilities. You either are 2, 5, 3, because you added 1 to the 2, and then you added a 2 on the left, or 6, 2, 2. And then you continue. So they are infinitely many, and in that way, you get all of them. So this is an easy way to recognize a wall singularity. Because here, so this, well, this is the -4 you started with. But now here, you have a wall singularity because you eliminate 2, 2. You get here from this 4 a 2, and then you eliminate this 2. You get from this 3 a 2, and then you eliminate this the 2, and you get from the 5 a 4. So you get here. So this is wall, this is wall. Well, actually, you can compute the continuous fraction and see that has the form that I told you here. And then so now we contract these two chains, so the two blue chains, and you get this cyclic quotient singularity and this other one that are wall singularities. So this is going to be my singular surface that is in the boundary. So you can prove that canonical class is ample for a general S that has that configuration, and that X1, which is this surface, has no local to global obstructions to deform. So we have a Q-Orenstein smoothing of this X1. So that means that locally on the singularities, you are using this deformation with Milnor number 0 for each of them, and they glue together to give a deformation of the projective surface, so that you can prove that the general fiber is going to be a Godot surface with fundamental group equals to Z over 2. So that is the first degeneration. And okay, so we have the picture. So this is my disk, and you crash into the boundary and get this X1. So now what happens is that if you contract, so now I go to the minimal resolution again here, but now I will consider this curve, this -1 curve, and I will contract it, and then contract, so I will contract the whole chain, -4, -1, 4, 5, 3, 2, 2, and then you get this singularity. This is a cyclic quotient singularity that is not wall singularity. So that is my surface, projective surface Y. The minimal resolution is this chain of P1s. And now it happens that I have another, well, maybe I should explain it like this. Here is the X1 from the beginning, this one, and where you contract these two chains, and you get these two chains, and these gamma 1 in between. Okay, this is going to be what we call an extremal P resolution over the cyclic quotient singularity. Okay, so this is the phenomenon that we want to search for in the surfaces in the limit, these KSBA surfaces with only wall singularities. A situation like this, and where you have a curve, a P1, that on the singularities is like a toric boundary, and this curve is positive for canonical class. And this is a P resolution, but it's extremal since we have only one P1 joining these two wall singularities. I will explain a little bit more in a moment, but now we would like to have another P resolution, and this is the other one. So it's very simple. Instead of so to get this one, you need to blow up, right? Right here between these -3 curves. But now we don't blow up. You go to the minimal resolution and you just contract 2, 3, 5, 3, 3. And that is another wall singularity. And now this -2 that you didn't use is going to be my Pi1, my P1, that constructs, if you want, the other P resolution. So we have two extremal P resolutions. So now we wonder what sort of surface is this? Is this a KSBA surface? And so one can prove that this X2 has no local to global obstructions, so we can deform, and in particular, we can Q-Orenstein smooth this singularity. And also, we can check that the K square and chi are the same. That is an easy check. But we don't know about the general fiber because it might happen, and it happens in this case, that canonical class for this X2 is not positive, it's not ample, not even F. And that happens in here, but if now you look at this gamma, this red curve, but on the singular surface, so here is, and you compute canonical class dot gamma, you get this negative 2 over 13. So that is bad, because then we are not guaranteed to be in the same modular space.
So it's some kind of a flip.
No, not yet. Now, so yeah, so we have this situation, we have this curve, and now we want to perform MMP, and we will use this curve. So here I have a reminder, go to Kollár. So let me go there. We have a little program to do the flip. So I can share also this link, so you can play with another flips. This is going to be very simple. Okay, so now you have this M, which is the index of the singularity. In this case is 13. So we have one wall singularity and this -1 attached to the wall singularity. And this is a flip situation where I have only one wall singularity. So I can use this K1A program. And then 13, and the other number I think is 8. So you add this. So now it has the singularity. If you remember, it's 2, 3, 5, 3, 3. And the -1 was attached to the 5. So I need to give the position of that curve. So it's 1, 2, 3, the position. So you put 3. And then this should compute the flip. So this is a flip situation, and now you have the flip. So it gives you the minimal resolution of the flip. And this -1 in between is the flipping curve. So the new curve that now is positive with respect to canonical class. If you want to play more, there you have the program. Now I will leave the program.
Which system is it written in?
This is Python. On the top, I think that you can check the system. Is that the question? Sorry.
Yeah. So it's not in Macaulay 2 or anything like that.
No. So I go down. So now we have this. So it turns out that we have this doesn't have any obstruction. So we have a Kuiper-Einstein smoothing of the X2. I haven't performed any flip. And now I do the flip, which is a K1A. And these flips were studied in my joint paper with Paul. I might be there, the audience, and Genia. And after the flip, we have the situation of X3 and a Kuiper-Einstein smoothing, where the singularities are now these two. And this was the information of the flip that I showed. And now you can go and compute, and now you can go and prove that the canonical class is now ample. And you know, when you do the flip, you don't change general fiber. So stay the same. And that means that if this is ample, we are in the same modular space, and we have a wormhole. So that is a wormhole. And we have the situation I was explaining at the beginning. It turns out, we don't really know how to deform, if you want, from X1 to X2. That is why X3, sorry. That is why we call it a wormhole. But it turns out, since this latest news, that they are deformation equivalent, but by other reasons. Okay, so now I want to explain the origin of these wormholes. So why we started to think about this. I hope everything is okay. Okay, so the origin of these wormholes. So you take a cyclic quotient singularity, is 1 over delta, 1 omega. So these are delta and omega, two integers, positive coprime. And you have the Hirzebruch-Young continuous fraction, P1 to Bs for delta over omega. But we don't care about that. We will go, okay, so if you want to get an extremal P resolution, you need to look at okay, that is later. You need to look at this fraction, this continuous fraction, which is now, so A1 to AR, and ask the following. So we have extremal P resolution. I will explain this part in a moment. If and only if there are two positions in these numbers, where you subtract 1 in those positions, and this continuous fraction is now a continuous fraction of 0. And that is the characterization of an extremal p-resolution for a cyclic quotient singularity, any cyclic quotient singularity. And maybe, as I said before, and now I am more precise, extremal p-resolution means a partial resolution of the cyclic quotient singularity where you have a p1 and 2 wall singularities, so that canonical class dot gamma, the p1, is possible. That is extremal p-resolution. P-resolutions in general were defined by Kollár Shepherd-Barron to describe all components of the space of deformations of a cyclic quotient singularity. So you have many components. It turns out that these components are labeled by p-resolutions, general ones, but these are the extremal p-resolutions, like minimal ones if you want. I think that you can characterize them as the ones giving you a smoothing of the cyclic quotient singularity with Miller number 1. Up to the node. Maybe you need to eliminate the node. You do eliminate the node. Up to that is Miller number 1. So you can ask that for any cyclic quotient singularity, but it might happen that you don't have only 1, as we saw in the example, but maybe you have 2. So this is again the example where you have the delta is 235, omega is 169. So this was the cyclic quotient singularity. You go to the dual, which is this. So 66 is just 235 minus 169. And now you can check that there is only 2 ways to find 2 positions where you subtract 1 so that you get 0 continuous fraction. So please stop me if you have questions. I'm very used to this, and I might forget about explaining something. And now you subtract here 1, here 1. I did that here, you see? Now it's 1 and 2. And well, what you can do to check that this is a 0 continuous fraction, you just go and blow down. You blow down this 1, and you get 1 here and 2 here, and you continue until you get 0. And the same happens if you do it in these 2 positions. So this is the other one. And of course, these 2 ones, see, this is the dot diagram to go from this to that. And if you do that, you get these 2 p-resolutions. So what happens is that if you have any cyclic quotient singularity, it turns out that you have only at most 2 extremal p-resolutions. And that is a theorem that we prove in this paper with Paul and Genia. And you can phrase it like this, only combinatorially. So let us consider a Hirschenbruch-Jung continuous fraction. This one, A1 until AR, where AK is bigger or equal than 2 for all K. And now we proved in that paper that there are at most 2 pairs, like I say here, so that you get 0 continuous fraction. So that means that you might have at most 2 extremal p-resolutions. And when that happens, well, we call this singularity a wormhole singularity. So that is the beginning of the wormhole situation. That is why we started to think about that. And then moreover, we can prove that, so if you take the continuous fraction in between, so you take what, maybe I can draw that. You take what is in between, see? So you go from the next position to the previous position of the AJ, and you compute this Hirschenbruch-Jung continuous fraction, you get delta K over epsilon K. So it happens, we can prove it, that the deltas are the same. And this delta is essentially, after you multiply by the indices, the intersection of the curve with the canonical class. and didn't have to be like that. We realized that this was happening with a computer, and then we proved it. So delta is an invariant of the anti-flipping family corresponding to the extremal P resolution. And you can check that in our paper. Okay, an observation is that with Nico Vilches, we have simplified the proof of one. So we reject these two statements. We gave a simplification of one, and we gave a new proof of two in the paper that we will put in the archive, I think, tomorrow. So we really think that this is completely true. We have double verification. Okay, so now we go to the conjecture. Maybe I will mention some support on the conjecture. So with Javier Reyes, that maybe is there, he's a student of mine, master student. Maybe he's there. Javier Reyes, we have a computer search for wormholes in PG0 surfaces where x1 is rational. And those are the dangerous ones. Those are the ones that might provide counterexamples. So it's very nice to search there. And we can check that it always happens. And we only need flips to find the stable replacement of the wormholing. So that is good. Okay, so now I will be precise with respect to the conjecture. So we start with this family, as always in this talk. So we have this family, Q-Garenstein smoothing, with only wall singularities, and assume that there is this extremal P resolution embedded. So like this. There you have it, and maybe you have more singularities. So you have the smoothing over a disk. And now let us assume that there is another extremal P resolution. So we have this situation of a wormhole singularity. So a cyclic Gaussian singularity that has these two extremal P resolutions. And X2, and we assume that it admits Q-Gorenstein smoothing, like in here. So our proposal, which is our wormhole conjecture, is that you might need to run here MMP, but when you run it, you only require to perform flips, and you will arrive to a minimal model. And if that happens, the KSBA replacement of this family will live in the same modular space as the original family. So that means you have the same invariants, but maybe you move to another component. That may happen. I will discuss a bit of that at the end. So under no obstructions, and precisely I mean this technicality, that is used in all these Lee Park examples, if you're familiar with those. And we have plenty of these situations of wormholes, okay, to check, but they are always, or almost always, very abstract, like I showed in the case of Enrique surface, that you have a configuration of curves, you prove that there are no obstructions, you have the smoothing, and so on. So one can reduce under no obstructions, like in here, one can reduce the conjecture to the case of a situation where you have extremal pre-resolution, but it is smooth outside. So like 2, 1, or 0 wall singularities. And now what we have so far is the following. So this is our theorem. Oh, maybe I'm going too fast. Do you have questions? So no questions. And so we can prove the following. If you start with a family where you have this X1, and say that canonical class is Neff even, and we have this extremal P resolution, so that you move to the other extremal P resolution. So maybe here the canonical class is not F anymore. But suppose that when you resolve singularities minimally, this gamma 2 becomes a -1 curve, like in the situation above. So that happens when you need really to blow up in a node in the cyclic quotient singularity that is below the two extremal p-resolutions. Okay, if that happens, and I'm sorry, this is a very important assumption, x1 is not rational. Okay, so and if it's not rational, one can prove that in the minimal resolution we'll have a minimal model. So we are not in the rule. We are ruling out rule surfaces. So it happens that you really need to blow up and you get a -1 curve in between. Then you can prove that there is not even need to do flips. Canonical class is Nef. So this is one. And in the second part of the theorem, again, you have the extremal p-resolution, canonical class is Nef, but now say that the other extremal p-resolution has a P1 with one wall singularity, and when you resolve minimally, a gamma 2, which is the P1 here, is a -2 curve. So a P1 with self-intersection -2. As you can see. Then canonical class maybe is not Nef, and this is exactly the case I was showing to you in the example at the beginning. So maybe canonical class is not Nef, but we run MMP only with flips, arriving to a minimal model. Okay, so those are the cases we can handle. I will show you what is left and some topology, which is related to whether we can move from one component to another. Well, maybe I didn't say much, but in the Godot surfaces case, well, we have this Misley conjecture, and we have a lot of wormholes for simply connected Godot surfaces. So it would be nice to to have a concrete example, maybe using wormholes, but well, we don't know how to do it. But that is part of motivation. But even you might move from simply connected to set 2, but I don't have an example to show you. Okay, so now I will talk about a bit of topology. So let us consider a wormhole between two surfaces, x1 and x2, having only two wall singularities. So we have only the situation of the extremal p-resolutions, and it's smooth outside. Okay, and now we look at the indices. Okay, so for a wall singularity, since I have time, maybe I can tell you more about wall singularities. So, you know, this is a wall singularity, and you have two of them maybe, and the index is exactly this n. So when you have these two, you have n1 and 2, and so this di will be the GCD of n1 and 2. And if you don't have two singularities, that means that n1 or n2 is 1 for us. So the GCD would be 1. So di will be 1 in that case. Okay, so let me show you an example where topology changes. What do I mean by that? So you have the smoothing of these two singularities, and now you have a smooth projected surface, some topology. And now I say that sometimes when you do this wormhole, in the wormhole, you are kind of changing the curve, passing through the singularities by another one. It's like a surgery. And so you smooth, and sometimes these two, the surfaces, the general fibers are not homeomorphic. So this is an example. You start with a elliptic fibration, like in here. This is a rational elliptic fibration with sections. So here I take one section, and you have two nodal fibers, I1, in Kollár's notation, I1, okay, or P1. And now we blow up on the nodes 3 times here and 2 times here. So you get 6, 2, 2, and this -1 curve, and then 5, 2, and this -1 curve. Okay, we have that. And now you can go and contract this 6, 2, 2, and the 5, 2, and so you get these two wall singularities. It turns out that this surface has no local to global obstruction. So again, we have a Q-Gorenstein smoothing. And that Q-Gorenstein smoothing is a Dolgachev's surface with two multiple fibers. So these are Kollár 1, Kollár equals to 1 surfaces with two multiple fibers. These are elliptic fibrations that have two multiple fibers with multiplicities 3 and 4. And so the fundamental group of this surface is trivial. So for this case, you have trivial fundamental group, so D1, and here the indices are 1, 2, 3, 4, like in here, 4 and 3. So GCD is 1. But here we have a wormhole situation. Although this is not ample, so I am not in the case I started in this talk, but still this is an example where you can see that topology changes. Now you contract the -1, this section, and so you get these 2, 2, 5, 4, 2, which is this. This is a cyclic quotient singularity that admits another extremal P resolution. So one extremal P resolution, so the first one is this one, 2, 5, and this -1 in between, and then 6, 2, 2. And now we have the cyclic quotient singularity, and we have another one, which is evident because you take 2, 2, 5, 4, which is a wall singularity. And then we are not using this -2 curve. So this is an extremal P resolution, another one. And in this one, you need to perform a flip. And why is that? It's because you free this -2 curve that you can see here. You know, this -1 that was like trapped between these two curves. Now it's only touching in here, it's only touching the -4 curve. So you have this flipping situation. Like, let me draw it here. Since I have time, I want to use my time. You have it like this. And now there is this -1 curve like this. And this is flip. So you can go to the program I showed you and do the flip. This is very simple flip. You see it, you contract and you get 2, 2, 5, 3. And now you just blow up this node and you get 2, 2, 6, 4, and a -1 curve in between. And that is the flip. And now there are no negative curves. You smooth, you get a Dolgachev surface, but now the multiple fibers are 2, 4. And if that happens, the fundamental group is set over 2. And so these two surfaces, the smoothings, are not homomorphic. And this happens in a case where D1 and D2 are not equal. So what happens if D1 and D2 are equal? Well, we can prove that the fundamental group, at least for general fibers, is isomorphic. This is a Van Kampen computation. It's not too difficult. And in fact, so one can prove that you keep the homology and intersection form. And so when you have this trivial by 1, by this Friedman big theorem, you get homomorphism. So that makes us wonder if this D1 equals D2 situation is special. So are the general fibers homeomorphic, diffeomorphic? We have something to say. And I point out here by these other reasons, by Diaz and Rito, that they prove that there is only one irreducible component, that was the case for the C2-Godot surfaces that I showed you. They are different. So when D1 and D2 are different, the situation like I showed in this example, it might be that they are not homomorphic, but it's not necessary. And again, it would be nice to know when, for sure, we cross components in these modular spaces. There is some criteria. And then I again say something about the Mice-Reed conjecture. So, okay, to end the talk. Okay. You have questions? I will say something about what is left on the question of wormholes. So for the non-rational case, what is left is to analyze these three situations. So the meaning of this is the following. You have a cyclic quotient singularity with two extremal p-resolutions that look like this. Wall singularity, a minus m curve in between, and then wall singularity. But these two walls are not necessarily the same. Just wall type, m, wall type. The same for the other one. For m bigger or equal than 2. So the point is the trouble for non-rational here, and for the other cases, A, B, and C, is to have some -1 curve, and I will show you an example, a potential counterexample for the wormhole conjecture. So it is to have a -1 curve that is attached to this -m in some way, producing no contradiction with this minimal model that I told you that we have when we have non-rational situations. I will show you an example in a moment. So we have this A that might be very messy. We need to analyze this. We don't really know how to understand this case, these cyclic quotient singularities with this type of extremal p-resolutions. And these other two, M wall, so here you have only one singularity, and here two, but you decrease by one the self-intersection. This is always the self-intersection in the minimal resolution. Or wall M and then M wall. And here we will have, I will show you a potential counterexample. But these two, I think that can be, at least the cyclic quotient singularities, maybe we have a better control with respect to the first one that might be chaotic. And for the rational case, so this is the dangerous one, we have only computed experiments. With Javier, as I said, we have several examples showing that this is happening. I want to check if Javier is here. Yeah, Javier is here. It's part of the audience. Okay. And so now, potential counterexample. What is this? So you have the cyclic quotient singularity. You go to 5. So this is like a symmetric situation. 5, 2, 2, 2, 8, and then 2, 2, 2, 5. So if you contract 5 until this 2, you get a cyclic, a wall singularity, because it satisfies the algorithm. So you eliminate 2, 2, 2. From 5, you get 2, and then 2, 2, 2, 2. From 8, you get 4. So you come back to 4. And this is symmetric, so you have it in the other side. So here you are in case C, for m equals to 5. This is one situation. And suppose that you have a -1 curve intersecting like this on an extreme. So you know, when you contract the left part to get the x1 situation, this -1 curve is not negative with respect to canonical class. So you can do the computation and you will see that it's not negative. But when you go to the other, then of course it's negative because it's not touching the singularity and it's a -1 curve. So actually, if this really happens, we would have the situation of a trivial divisorial contraction. You have a -1 curve not passing through singularities. You have a deformation, so it leads to a -1 curve on the general fiber. You have a divisor to contract. So we would be in trouble because you would change k squared. So you would be in another modular space, or maybe you get rational. There are several possibilities. But we don't know if this really happens. This is only combinatorial. So it's not only, to have this counterexample, it's not only that you have this situation in some surface, that you need to have the smoothing and everything, but also to have canonical class sample for X1, you need to make sure that you don't have other -1 curves bothering. For example, you cannot be like symmetric and having like a -1 in here, because that is not allowed, because it's sample the X1 side. So only here. And also you cannot have like a -1 touching this -5 and touching one curve in between, and so on. So it's not only about this configuration, but to start with, we need something like this. Okay, so last curiosity about this, and this is kind of combinatorial. So it seems like this delta, this invariant for a wormhole singularity. So again, wormhole singularity means cyclic Gaussian singularity with two extremal P resolutions, where we have this delta that might be different, right? But we prove that they are equal for both. So it seems like when you have a wormhole singularity, this delta is not any integer. So there is a special set of deltas. If you have only one extremal P resolution, then delta could be anything. And I can show you examples. It could be any number you want. But when you have a wormhole singularity, it seems like it's a particular set, but we don't know how to describe that set. And here I have a list of numbers when you consider two extremal P resolutions, and one of them has this form, a -2 and then 1. So if you look at the preprint that we will put in the archive, you will see more values. And there the question is, what are the possible values for delta in a wormhole singularity? And well, I will have 11 minutes for questions, because this is the end. Thank you.
Okay, thank you, Giancarlo, for a very nice talk. And we do have time for questions, comments.
Hey, this number D, the GCD of N1, N2, I guess that's just the fundamental group of the Milnor fiber when you smooth this B2 equals 1 smoothing.
Yes.
Yeah.
Yeah.
But you say if the fundamental group of those two Milnor fibers is the same, then you can prove the fundamental groups for the global.
Yeah, the global thing is the same.
Uh-huh.
And when it's different, maybe it's the same, maybe it's not. We don't know how to control that.
Cool.
You look very well in the
Sorry?
video.
Oh, thank you. Nice to see you.
Nice to see you. Yeah, sorry
Why
if
do
I-
you think the delta is has restrictions?
Well, maybe, no, that is, it's just because of computer search. It's not because we don't have any other reason. And I think that we can prove for delta equals to 3 that is impossible. So, but we haven't looked too seriously at this yet. It's only that the computer is giving us a specific list. And when you have only one extremal P resolution, delta could be anything. There is something special about these wormhole singularities. So sorry, maybe it was a lot of too much information, but you will have the preprint maybe for the next day.
Other questions?
I have a little question. Giancarlo, you did this procedure. You did this procedure for wall singularity. Is it possible to do also for general T singularity or not?
Well, for wall singularities, so extremal P resolutions have these wall singularities. For P resolutions, you might have a similar situation, but I haven't thought about that. So we are like in a minimal case and try to understand what is going on. But with P resolutions, you have T singularities, and well, at the end of the day, everything can be reduced to wall singularities. That is.
Yeah, I think
Because
so.
you have these M resolutions. But yeah, this is for this extremal.
Another comment that if you have a cusp singularity, then that can have many smoothing components as well. And you could, so that actually that one you could just have it in literally in the boundary of KSBA. You could have a surface with K ample and a cusp singularity that has several smoothing components. So you wouldn't have to do any birational modification to begin with. Mm-hmm. And you could ask if you get, if you can walk around in the moduli space that way as well. I don't actually know, can you get a cusp singularity on a PG = 0 surface? Do you have any examples?
I don't remember, but maybe I don't have.
I mean, the sort of Hodge theory picture there, you tend to reduce PG by 1 when you get a cusp singularity. Mm-hmm. But I think, I mean, certainly there are examples of PG0 surfaces with simple elliptic singularities, right? So it doesn't preclude it, it just means it's a bit less likely. But if you had such an example, you could sort of do the same thing, glue in different Milnor fibers, you might be able to get to some different components.
Thank you for that. Maybe Sonke knows some example, I don't know if Sonke is there, or Rita. Well, I don't remember.
I have already started looking it up. I mean, we had some classification of Gorenstein stable Godot surfaces, and I was just opening the paper and seeing if what's in there, if there is a cusp there or not. But I can check. If I find one, I'll tell you.
Yes, I was trying to do the same of Zonke.
Are there any other questions or comments?
Yeah, so in the beginning, you said something about new developments on Godot surfaces. What?
Yes.
Not about your talk, so I don't know if you want to say anything.
So maybe you can send the preprint. So Carlos and Diaz, they found out how to manage the computation of these moduli space for set 2 Godot surfaces. And that was last year, September. And so now it seems like my street conjecture is true for 2, 3, 4, and 5. And this is computational and it's hard. I don't really can go to details there. And this happened after we worked together on these limits of set 2 Godot surfaces. So we have like 11 options, and we don't know if all of them are realizable. And then that is another paper a year ago, and this is from September.
Just to find a very quick comment. I looked in the paper. There are no, if you stick to Gorenstein stable Godots, there are no cusps, only simple elliptic singularities. So it's, I don't know, proposition lemma 2.2 in our paper.
And which one? Which paper? Can you send?
Gorenstein stable Godot surfaces.
Okay.
I can send you the link. I put the link in the chat.
All right. Thank you.
So if there are no further questions or comments, I'd like to again thank you, Giancarlo, for a very nice talk. And the next talk is at 1:30 Miami time. Thank you.